picture this. It's 1987. Doctors have these incredible brand new machines, CT scanners, MRI scanners, that can literally peer inside the human body. The catch? What they get is just a big stack of flat 2D pictures. So how in the world do you take that stack of slices and turn it into a real 3D model you can see, rotate, and truly understand? Well, today we're diving into the brilliant, game-changing algorithm that solved that exact problem, marching cubes. All right, so here's the plan. First, we're going to really get a feel for the problem doctors were up against. Then we'll take a quick look at the kind of clunky solutions they had before this big breakthrough. After that, we'll unpack the sheer genius of the marching cubes algorithm itself. And finally, we'll see the absolutely stunning results and talk about its incredible, lasting legacy. So, let's set the scene. The entire world of medical imaging was right on the edge of a massive revolution, but it was missing one crucial ingredient. This was the million-dollar question. I mean, sure, a skilled radiologist could painstakingly flip through, 100 different 2D scans, trying to mentally piece together a tumor or a complex fracture in their mind, but then trying to explain that 3D shape to a surgeon, that was next to impossible. What they needed was a way to automatically take that stack of images and turn it into a solid, tangible object right there on a computer screen. And this is what they were hoping for, something just like this. See, in 1987, two engineers from General Electric, William Lawrenson and Harvey Klein, published a paper with a truly revolutionary solution. They figured out a way to create images with this level of quality, and it completely unlocked a new era of medical visualization. But to really appreciate just how big a deal this was, we gotta look at what came before. Yeah, before marching cubes, researchers had a few ideas floating around, but they all had some pretty deep flaws. They either missed a ton of crucial detail or created visuals that just weren't realistic enough to actually be used in a hospital. Basically, there were two main approaches. The first, contour algorithms, was really just a high-tech game of connect the dots. You trace the outline on one slice, trace it on the next, and have the computer connect them. It worked okay for simple shapes. But what if one slice had, say, two different bones showing up? The algorithm would just get totally confused about how to connect them. The other method, cuboreal models, was kind of like building the anatomy out of Legos. It gave you this rough, blocky shape, but as the original paper puts it, these methods would throw away useful information, losing all that fine, critical detail that doctors desperately needed. And this is where Lawrenson and Klein enter the picture, with an idea that was just so powerful and incredibly clever. They called it marching cubes. It was designed from the ground up to be a high-resolution method that didn't throw away data. Nope. Instead, it used every bit of information in the original scans to build a detailed, smooth, and really accurate model out of tiny triangles. This was the elegant solution the medical world had been waiting for. So, how'd they do it? What was the secret sauce? Well, the genius of marching cubes is really its divide and conquer strategy. It doesn't try to solve the whole complex 3D model all at once. Instead, it breaks the massive problem down into millions of tiny, simple decisions. Okay, so this is the high-level recipe right from their paper. Now, don't worry, we're not going to get lost in every single technical detail, but the core idea is actually pretty simple. The algorithm looks at a tiny chunk of data, creates a little imaginary cube, figures out exactly how the surface of what you're looking for, like a bone, cuts through that one cube, and then it just marches on to the next one, stitching all the results together as it goes. Let's really focus on that core idea. Imagine a tiny little cube. It's defined by just 8 pixels, 4 from one of the medical scan slices, and the 4 pixels that are in the exact same spot on the slice right below it. That's it. The algorithm's entire job, repeated millions of times, is to figure out what piece of the 3D surface exists inside this one tiny logical cube. And it does this by asking a really simple question. Based on a density value, like the known density of bone, is each of the cube's 8 corners inside the bone or outside the bone? It's just a simple yes or no for each corner. The surface that we want to draw has to pass through any edge that connects an in corner to an out corner. Simple as that. Now, here's where your brain might start to hurt a little bit. With 8 corners, and each one can be either in or out, well, that means there are 2 to the power of 8, or 256 different ways that a surface could possibly slice through this one little cube. Trying to calculate the geometry for all 256 of those possibilities on the fly for millions of cubes, that would have been computationally brutal back in 1987. And this right here, this is the brilliant shortcut. This is the aha moment that Lawrence and Klein had. They realized that through rotation and reflection, all 256 of those complex cases could actually be boiled down to just 14 fundamental patterns. Just 14. So they pre-calculated the right triangle shapes for those 14 patterns and just stored them in a lookup table, like an answer key. The algorithm just figures out which of the 256 cases a cube is, and then it just looks up the pre-solved answer. It's not about raw power, it's about a super clever, super efficient lookup. So what happens when you apply this incredibly clever logic millions and millions of times across an entire medical scan? Well, you get something that looks a lot less like data and a lot more like a sculpture. And I mean, just look at these results. These images are pulled directly from the original 1987 paper, and they were all generated from a single CT scan of a person's head. By just setting the density value for bone, the algorithm generated this incredibly detailed model of the skull. Then, using the exact same data, they just chose the density for soft tissue instead, and it generated this model. The power to just isolate different structures with this kind of detail was absolutely revolutionary. And just to give you a sense of the sheer resolution we're talking about, the paper notes that this bone surface model was constructed from over 500,000 tiny triangles, 550,000. Each one was perfectly placed and shaded based on the original data. This wasn't a blocky approximation. This was a high-fidelity digital reconstruction. And the legacy of this idea is, well, it's immense. The basic concept of marching cubes, of turning this grid of data points into a 3D mesh, it's foundational to so much of the 3D world we see around us today. It's used in modern medical imaging for planning surgeries. It's working behind the scenes in 3D printing. It helps scientists visualize incredibly complex data, and variations of it are even used to generate realistic terrain in video games. You know, the 1987 marching cubes algorithm gave us a window into the human body, a world we couldn't see before. It took abstract numbers, density values, and turned them into a world we could actually see and explore. It really makes you wonder, right? What other invisible worlds hidden away in financial data or climate models or social networks are just waiting for their own version of marching cubes to make them visible?